Hey guys, Lenny Reed, Dynamite Diesel Products. I want to talk to you today about some P-pumps. There's 4 different P-pumps that came out in the Dodge pickup trucks. There's lots of other hot rod race versions available after that. And proper injection sizing, proper turbo sizing, piston bowls, things like that. Really specific towards like 12 valve guys. Now, we've got this custom injector order form. On this form, it asks you name, desired horsepower, elevation, what you're doing with the truck, street strip toy, 1992, what you've already done to the truck, pistons, head gaskets, all these things. It's kind of important because if you're living in a really high elevation or really low elevation, you're going to get 2 different recipes. If it's a sled pull truck, you're going to get a different recipe than, say, if this is a 2.6 truck that's supposed to make like 1,200 horsepower, and you're trying to drive a street truck at 1,200 horsepower, 2 totally different injectors, and probably 2 totally different injection pumps as well. So, custom injector order forms on the website. This does not make you purchase a set of injectors, but when you take the time to fill this out, we take the time to read through it and decide what is going to be the best thing for you to make sure you get something that's going to do the job that you're after. Okay, so custom injector order form, 1 is done. 2, 160, 175 horsepower pumps, 94, 95 auto and stick trucks. Those camshafts don't offer a lot of fill time. So at low RPM, 1,000, 1,500, 2,500, the camshaft is pretty okay. They run fairly quiet because there's not a lot of ramp rate, so the injection pressure is kind of low and slow. But when you rev those things up, you put governor springs in them, they will not respond to a governor spring like the other style out of a 180 or a 215 style cam would. Why is that? Again, the fill time that's built into the camshaft, it doesn't have a lot of fill time. So as you ramp up the engine RPM, you decrease the time in which you have to fill the chamber above the plunger. Therefore, the higher you rev it, the less fuel there is sitting on top of that plunger. So 160, 175 is not my favorite, and if you're looking for like 450 horsepower or more, I would recommend that you start by trying to find yourself a 215 style pump core, or we can get you a reground cam. There's a lot of people that offer reground cams for those pumps. You can get a 215 style plunger. Those plungers will offer double the amount of fuel on a test stand, and if you set like 215 pumps at 15 degrees static timing, 16 millimeters rack travel, you gain 2 degrees. 17 millimeters of rack travel, you gain 2 more degrees advance. You can do that all the way up to 21 millimeters of rack travel, and your timing goes up progressively based off of rack travel. So that is what they would call a retard style or a notch top style plunger. And it does retard. As you get out of the gas pedal, the timing retards again, but as you stand on the gas pedal, it starts to give you more advance. Contrary to what a lot of others would let you believe or want you to believe, but they really run fabulous on the street. So, injection nozzles, injection nozzle sizing. P-pump guys are horrible about, like, they've been told to buy a 5x12 or a 6x12 or a 5x18. That's probably one of the most common ones that's out there. If you have a 5x18, that is a huge hole, and if you've put it on something with a very small plunger, like a 160 or 175 or 180, you're never going to get the gain out of that 18 thousandths hole that you need to. With holes, I'm going to let green screen help me out here. So with this right here, this is an image of a stock nozzle with just EDMing done. Back in the day, there was no AFM, there was no Extrude Home, so that's what we made. This is going to be like a 370 marine nozzle right here. This is, tested by the government. This was manufactured, and there's hundreds of thousands of these in use right now. The next image, same nozzle with pilot hole technology and with AFM run through it. Now, this next image is no pilot hole. This is what we used to do with just Extrude Home stuff. You'll notice that those 3 images, one, there's no K factor. You've kind of got that reverse welding looking process, kind of a black scaly finish. We've got a really nice K factor that's very sharp and over the edge. It acts like a velocity stack, so when the needle valve goes to lift, the fluid is shoved down into those holes, and that velocity stack enhances the speed that it breaks the outside face of the injection nozzle. And then Extrude Home. What we were doing for a long time was we were taking Extrude Home media and we were trying to blow the hole open and make it bigger and make it flow more. And the more K factor we added to it, the more gross volume we got out of it. But when you do only Extrude Home, you take the depth of that nozzle. So nozzle thickness is about 47 thousandths thick. We want most of that K factor done within the first 4 or 5 thousandths of an inch. And we want the bore to stay very, very true and very, very straight, because then we're actually going to penetrate into the pocket of the bowl of the piston bowl. This diameter that we're talking about, that bowl, you want to put the fuel as close to the piston as possible without any liquid hitting the piston. If you get piston that sees liquid, that'll generate a lot of heat, and when that melts off of there, it's going to literally melt the piston right off. So we don't want that at all. Now, with P-pump style stuff, your injection pressure is much lower than, so we're going to set the opening pressures at 270 bar. 270 bar is like 3,916 psi. You look at a common rail, and every common rail will idle at about 5,500 to maybe 6,000. And if you make a common rail a really big nozzle, get it to where it's got spray holes that are 12 or 13 thousandths, even bigger, you're going to see that your tuners will start increasing the idle pressure to help atomize those things and get them to run clean at idle. So P-pump pressure, very, very low. When you stand on the gas pedal, you may see as much as 10x at wide open throttle for injection line pressure as you do at idle. But remember, you've got about 3,900 psi at idle, and when you stand on the gas pedal, you might see 10x. So you potentially could see 39,000 psi of line pressure for a momentary burst when you're at wide open throttle if you've got a huge injection pump and a very small injector. Now, what happens to injector lines and plungers if you're actually going to sustain, 39,000 psi? Well, the plungers are going to get stuck. That's going to hang the rack travel open, and you're not going to be able to get the gas pedal to come back to zero. The pump will run away. That's a bad deal. So that's number one. Number two, the injector lines will start to crack and fail very, very frequently. Now, a lot of guys will elect to run a larger diameter line, and I want you to think about the line in this manner. That line is an accumulator. So there's nothing really stored in the line. Once the delivery valve goes to open, the line is going to get charged with fluid. The smaller that the diameter is, the faster you're going to hit that injector. The larger the diameter, the more of the accumulator you have to fill before the spring starts to chatter from pressure. So you're going to get a retarded timing event, and you're going to want to make sure that if you're going to run a bigger line, that you do so on the dyno so you can actually adjust timing, find out where it starts to fall on its face, and then pull timing back. Don't take your buddy's word for it and be like, just buy some 105 lines and it's going to run great. It's not going to run great. You're going to want to rent a dyno for a couple, 2 or 3 days to make sure you get those lines dialed in with your thing. When I say your thing, if you've got a flat top plunger, you might get 400, 460 cc's out of it. If you've got a notch top style plunger, you might get 800, maybe 900 cc's out of it. If you've got a 13 or a 14 or any of the even bigger plungers, you may get a lot of delivery out of that. But the next question for you is going to be injection rate. So the camshaft underneath the plunger and underneath the delivery valve, the camshaft is responsible for how fast you get to hit that nozzle and how fast you get to pull off. So beginning, or BOI, beginning of injection, is based off of spill port goes to close and fill port goes to close. Plunger rises above that and it creates pressure. Fluid does not compress, so it goes towards the delivery valve. Delivery valve spits it towards the nozzle. Nozzle chatters. Nozzle gets done chattering as soon as that plunger drops back down, and you've lost all your injection flow and it moves to the very next cylinder. Ramp rate on camshafts. There are stiffer springs that will help control all of that as it's happening, because you've got ballistic things going on. There's so much violence, there's so much injection pressure happening right now and releasing right now, that if you're going to build the pump, there's some really good pump builders out there, and they're going to do a lot of things that are going to help keep that pump alive for performance applications. Dual feeding it, DLC coating the plungers, all sorts of different things. Just because your pump can pump 1,000 mm cubed or 1,000 cc's of delivery does not mean that you're going to use all of it. You may find that because of air-fuel ratio with AFR, you're going to make your optimum power with your turbocharger and your injectors at, say, 580 cc's, 590 cc's, maybe 650, maybe 700. I don't know. I don't know what your recipe is. I don't know what your setup is. But with all the mechanical style pumps, it's basically as easy as changing out delivery valves and changing out cam plates or adjusting the fuel plates and limiting your fuel based off of those things. Again, dyno time is critical. I would advise anybody that's going to build a real hot rod to rent a dyno for up to 3 days, because day number one for me is always exploring what I have for parts, getting a few baseline hits, making some really big swings, and trying to get myself in the ballpark. Day number two, we usually get on the scent, and we usually get pretty close to where the thing's going to run really good, not make a bunch of exhaust gas temperature, but by now we've already adjusted timing, we've adjusted injectors, we've done a lot of things to get this thing, to really get the dog on the trail and get on the scent. Now, day number three, we're probably going to try a few more things and we go backwards. But since we've documented and we've got good notes on what was working really well, by the end of day three, we're back on that trail and we're just honing in very closely on very small tweaks to whatever was best. So if you've got a set of 5x18s on a 160 horsepower pump, you're going to have a hot smoky mess forever because the volume that hits the injector is not enough. You could probably get away with a stage 1 or a stage 2 injector and make a lot more power and a lot more drivable power, especially with pilot hole technology, because what that does is you've got, let's say your hole diameter is 12 thousandths of an inch and it's got K factor, so that hole is very efficient at flowing diesel. Now we come in behind that and we put two holes closer towards the piston at 50% of whatever that hole diameter was. The reason we do that is because at low injection pressure, again, you're going to be idling at like 3,916 psi. At 3,900 psi of idle pressure, 12 thousandths holes are really big. They're going to be a little bit sloppy. So when we go in with two pilots right behind that, now you're idling through two holes that are, say, 6 thousandths of an inch. Well, path of least resistance is where the fluid's always going to go. So once the demand, meaning your foot, stands on the gas pedal, you're going to overcome those two pilot holes. They're not really going to do very much at all. But prior to making boost, prior to making a lot of injection pressure and pumping a lot of volume, those two little pilot holes really help atomize and get the burn going cleaner. So it's just a hydro mechanical pilot invent is all it is. With P-pumps, there's really no way to put pilot injection in, but you put pilot on a power stroke, you put pilot on any common rail, and they're very responsive and they drive really good off the bottom end. We're just doing that to the injectors on the P-pumps. So for guys out there that are wondering, like, what's Dynamite doing differently than everybody else? A lot. We've got dual feeds, we've got pilots, we've got AFM versus Extrude Home, we've got the EDM, so we can choose hole diameter within 1/10 of 1,000th of 1 inch. So we start with a blank, we're going to find the angle and the hole count that's optimum for your piston diameter. Once we do that, we figure out what hole diameter we want to use. So if I'm going to use a 10 thou piece of wire, by the time I burn through the nozzle, now we've got 47 thousandths of an inch of rifle barrel that we've angled at your piston bowl. That 47 thousandths of an inch on a 10 thou piece of wire is going to be about 11.1, 11.2, 11.3 for a hole diameter. Then we're going to run to the AFM or the Extrude Home. And the reason that we have both those machines still running right now is because abrasive flow machining is it's a liquid type compound, and you know, like in the old fellas in this industry will call that they'll call that the slurry, meaning it's just liquid. It's got suspension of abrasive flow stuff in it, and we have an agitator in the tank that's constantly keeping that stuff floating. So when we turn the AFM on in the morning, we run that for about 20 to 30 minutes to warm up the fluid. And in the fluid, we've got to agitate all of the cutting agent and suspend it in the fluid. So when it pumps through the nozzle, we get consistent results all day long. The second material, or the older material that we've always used, was Extrude Home media. And Extrude Home media is a lot like children's Play-Doh, silly putty, that kind of stuff. There is a cutting agent that's suspended in it all the time. You don't have to mix it. You don't got to do anything like that. It runs, it's a lot like if you go to a body shop. When you go to a body shop and you do the initial construction or reconstruction of the vehicle, you're going to lay out your Bondo, you're going to hit it with, like, say, a 36 grit, and it's going to be a real rough, abrasive, and fast cut. With Extrude Home media, we can get stuff that's a lot like that. Then it goes from the real rough cut 36 grit to like an 80 grit, which you're going to hit with your primer. You're going to clean up the primer as fast as you can with 80 grit, and then you may go to a 240, and that's going to be an even slower cut. And then finally, after paint, you're going to have your clear coat. You might hit that with a 2000 grit piece of sandpaper. Extrude Home media is a lot like that. We've got different medias for different hole diameters and different finishes on different cuts. So Extrude Home is something that we've used for 20 years-ish, and we've gotten really good with it. AFM is a bit more accurate, and especially on the later style stuff, the AFM really shines very, very well because those really small holes. Common rail stuff today, we've got stuff that's down around 5/1000ths of 1 inch, 4/1000ths of 1 inch. Extrude Home media would be so big and so blocky that it would plug those holes quite often, and the AFM not necessarily so much. So with all three of those techniques at our disposal right here in this building, we can basically build you an optimized part every single time. With our stuff, we offer a DLC coated needle valve. You may notice that with DLC coating on the needle valve, it's a little bit smoother and a little bit quieter to operate. Reason for that is because that DLC coating is very, very slick, and the speed in which that needle valve is traveling is a little bit sharper than if it's just steel on steel contact. So why did we do that? Well, number one, because DLC is a new thing for you guys out there in the industry that have never run a DLC coated part. They should last longer than anything that's steel on steel, but the speed in which we can turn the injector on and shut the injection off, I really wanted to make that just as precise and clean as possible. DLC helps us control that just a little bit. So that's kind of why we do the DLC. Now, I do want to talk to you about like vortex flow and a cavitation. So vortex flow, when we create the K factor and we give the fluid a nice smooth cylinder to flow through, you get a vortex flow. Vortex flow is optimum. That's what we want. That's what we're after. You're going to get great atomization. You're going to get really good throttle response, good mileage, good smoke control. If we have a cavitation style flow, you don't have enough injection pump. Your spray hole is going to be something like this right here, which is EDM'd, but it's not our EDM. This is something that was done at another place by other people, and this is horrible. Like, you're not going to get fluid to flow through anything like this and have it atomize very well at all. So you might get a lot of gross quantity because the hole diameter is so bloody big, but start ability is garbage, drive ability is garbage, coming off a stoplight or a stop sign, garbage. Fuel economy, garbage. If you're leaving trails of black smoke behind you when fuel's $5.50 a gallon, you're kind of crazy. You don't have to do that to make optimum power. When you've got a hole this big, your air-fuel ratio is going to be really, really rich. So as much air as you're pumping into the motor, you're pumping out too much fuel to get that motor to burn efficiently. So AFR is just too rich using a hole like this. With hot rod guys, let's talk about like piston bowls and what piston bowls do for you. There's a couple of really popular ones. Like, you've got the standard bowl out of a Dodge pickup truck, which standard bowl, small diameter, compression ratio is going to be close to 17 and a half to 1. Very, very nice to drive on the street. If you use really good hardware when putting the motor together with really good clamping loads, you can use a 17 to 1 motor, clear up to 1,000 horsepower, and it's going to be super spunky with lots of throttle response. You may elect to use the marine style bowl, which is that guy. I'm so excited to have this green screen, you guys. Like, being able to show you what I'm talking about on the drop of a hat, perfect. What's cool about these things is when you put them in the boat, when you put them in something, say a tractor, where you drop a plow and you're going to go maximum load for 8 to 10 hours a day, Losing 2 points of compression does not affect you in any way negatively, but when you use a 15-to-1 piston on the street, you'll notice that exhaust gas temperature under the boost curve is going to be hotter than it used to be because you don't have enough squeeze there to burn all the fluid that you're shoving down its neck. You're going to notice that fuel economy is going to be worse because you're not squeezing all the fluid and burning all the fluid when you should be at lower throttle positions. Where these things really shine is basically that 1,000 horsepower and above. Big turbos, big pump, big injectors, and it's a vehicle that's being built specifically to take a beating over and over and over, and you don't really street drive it. Head gasket thicknesses. There's a 10 and a 20 and I believe a 30 thou thickness head gasket for 12 valve trucks. And the reason you would do that is those motors, if the head was warped, you lost the head gasket, you left it running, the head gasket, all the coolant and such, would then destroy and distort the top of the block. So piston, if you've ever torn a motor apart, you'll know that when you roll the motor over, the piston will protrude above the deck. We measure that, and that's called piston protrusion. That piston protrusion gets consumed in the thickness of the head gasket. If you have to deck 5 or 10 thousandths off of the block, instead of cutting pistons, you can elect to purchase the thicker head gasket to make up for the material that you've removed off the block to get the block straight again. If you've got, say, 25 thousandths piston protrusion on a 12 valve, you're in pretty good shape. If you put a really thick head gasket on that motor, every 10 thousandths that you increase head gasket thickness, you decrease compression ratio by about 0.3 of 1 point. So if it was a 17.5-to-1 motor, you add 10 thousandths thickness, you're now going to be really close to about 17.2. That's not going to run poorly, but now you've also messed with geometry of nozzle protrusion and the pocket of the bowl. So now where the nozzle used to be very close and designed and aimed right at that bowl, you've lifted the nozzle, you've pulled the nozzle away from that bowl, and you're going to be breaching outside of the pocket and on the top of the piston at an earlier time. When you set your injection timing, if you set it at 17 degrees, you used to be in the pocket, you add 10 thousandths, 17 degrees might bring you out of the pocket and start spraying above. So those are things that need to be considered as well. What can you do to offset that? Well, the nozzle nut itself, we can machine 10 thousandths off the nozzle nut to bring it back down to its original geometry. Coppers, there's a 2 millimeter, there's a 1.5, and there's a 0.5 millimeter copper. All of those things can be considered, and with that custom injector order form, when you let us know what you've done to your motor, we can help you make the right decisions on all those things. So before I get too much longer and too much deeper on this video, I don't want to bore you guys or bury you with too much, but I hope this helps everybody with 12 valve stuff. And again, Lenny Reed, Dynamite Diesel Products. Later!